When dealing with high voltage conductors, specifically 19.8 kV primary conduits, passing through a chiller pump room, there are specific requirements outlined in the National Electrical Code, NEC, and the IEEE standards that must be followed. NFPA 70, the National Electrical Code, in section 450.21. B1 addresses conductors located in a room used for the purpose of conditioning air or housing air handling equipment. This section states that such conductors shall be encased in not less than 2 inches of concrete. The IEEE 45, recommended practice for electrical installations on industrial and commercial properties, specifically section 6.3 2.14, also known as the Green Book, provides additional guidance. It stipulates that primary conductors in electrical rooms shall be encased in not less than 2 inches of concrete from the floor line to a height of 2 feet above the equipment, or as per the authority having jurisdiction. Applying these standards to the situation of running 19.8 kV primary conduits through a chiller pump room, it is essential to encase these conduits in concrete from the floor line to a height of 2 feet above the chiller pump equipment. This encasement serves as a protective measure, safeguarding the conductors from potential damage that may arise from the operation of the pumps and other equipment within the room. It is crucial to consider several additional factors to ensure the effectiveness and longevity of the concrete encasement. Firstly, the concrete encasement should be poured in a manner that prevents the trapping of moisture or the creation of voids within the encasement. Moisture and voids can compromise the integrity of the concrete and potentially lead to corrosion or structural weaknesses. Secondly, the concrete encasement should be adequately protected against corrosion. This can be achieved through the application of a concrete sealer or a specialized coating designed to resist corrosive elements present in the chiller pump room environment. Thirdly, the concrete encasement should be engineered and designed to withstand the weight of the conduits themselves, as well as any equipment that may be mounted or supported by them. Structural integrity is paramount to ensure the safety and reliability of the installation. Fourthly, the concrete encasement should be designed in a manner that allows for accessibility in the future, facilitating maintenance activities, inspections, or any necessary modifications to the electrical system. Accessibility is essential to minimize downtime and ensure efficient operations. It is highly recommended to consult with the local electrical inspector or the authority having jurisdiction to gain specific requirements and approvals pertaining to the installation. Local regulations and interpretations of the national codes may vary, and adherence to these local requirements is crucial for compliance and safety. Now let's delve deeper into the technical aspects of concrete encasement. Firstly, the type of concrete used for encasement is important. It should be a high-quality concrete mix designed for electrical applications. This type of concrete typically has a low chloride content to minimize the risk of corrosion to the embedded conduits. Secondly, the thickness of the concrete encasement should be uniformly maintained at a minimum of 2 inches, as specified by the codes. This ensures adequate protection against physical damage and electrical hazards. Thirdly, the reinforcement of the concrete encasement may be necessary, especially for larger conduits or when the encasement is subjected to significant mechanical stress. Rebar or wire mesh can be used to enhance the structural integrity of the encasement. Fourthly, proper grounding and bonding of the conduits within the concrete encasement is essential for electrical safety. Grounding conductors should be securely connected to the conduits and bonded to the building's grounding system. Fifthly, the installation of expansion joints in the concrete encasement may be required to accommodate thermal expansion and contraction of the conduits. Expansion joints prevent cracking and damage to the concrete due to temperature fluctuations. Sixthly, the concrete encasement should be adequately cured after pouring to achieve its full strength and durability. Proper curing involves keeping the concrete moist for a specified period of time, typically 7 days. Seventhly, the surface of the concrete encasement should be smooth and free of sharp edges to prevent damage to the conduits during installation or maintenance. Eighthly, the concrete encasement should be clearly marked and labeled to indicate the presence of high-voltage conduits. This helps to prevent accidental damage during future construction or maintenance activities. Ninthly, regular inspections of the concrete encasement should be conducted to identify any signs of cracking, spalling, or corrosion. Any damage should be promptly repaired to maintain the integrity of the encasement. 10thly, consider the environmental conditions within the chiller pump room. If the environment is particularly corrosive or humid, additional protective measures may be necessary, such as the application of a corrosion-resistant coating to the concrete encasement. Now let's address some common challenges encountered during concrete encasement installations. One challenge is the presence of existing utilities or equipment in the vicinity of the conduits. Careful planning and coordination are necessary to avoid conflicts and ensure that the encasement can be installed without disrupting existing services. Another challenge is the limited space available for the encasement. In tight spaces, it may be necessary to use specialized formwork or pouring techniques to achieve the required concrete thickness. A further challenge is the potential for moisture to accumulate within the encasement. Proper drainage and ventilation should be provided to prevent moisture buildup. It is also important to consider the impact of the concrete encasement on the overall aesthetics of the chiller pump room. The encasement should be designed and installed in a way that minimizes its visual impact and integrates with the surrounding environment. In summary, encasing high-voltage conduits in concrete within a chiller pump room is a critical safety measure that requires careful planning, design, and execution. By adhering to the requirements of the National Electrical Code, IEEE standards, and local regulations, and by considering the additional factors discussed above, it is possible to create a safe, reliable, and long-lasting electrical installation. Remember to always consult with qualified electrical professionals and local authorities to ensure compliance with all applicable codes and standards. Now consider the specific situation where the transformer is on an elevated deck above the chiller pump room. In this case, the two 6-inch rigid metal conduits, RMC, will pass vertically through the chiller pump room to reach the transformer level. The secondary conductors will then return down into the chiller pump room to supply the starters. Given this configuration, the concrete encasement should extend vertically from the floor line to a point at least 2 feet above the highest piece of equipment in the chiller pump room, including the chiller pump itself. This ensures that the entire portion of the conduits passing through the room is protected. The encasement should be continuous and without gaps or openings, providing a complete barrier between the conduits and the surrounding environment. In addition to the vertical encasement, consider providing a horizontal concrete pad or support at the base of the conduits to distribute the weight and prevent settling. This pad should be of sufficient size and thickness to support the conduits and any associated equipment. When the secondary conductors return down into the chiller pump room, they should also be protected in accordance with the National Electrical Code. Depending on the voltage and ampacity of these conductors, they may need to be installed in conduit, cable tray, or other approved wiring methods. Ensure that the secondary conductors are properly sized for the load they will be carrying and that they are protected by appropriate overcurrent devices. Also, the starters for the chiller pump should be located in a safe and accessible location within the chiller pump room. The starters should be protected from moisture, dust, and other environmental factors that could damage them. Consider using enclosures that are rated for the specific environmental conditions of the room. Moreover, regular maintenance and inspection programs for the entire electrical system, including the conduits, concrete encasement, and starters, should be implemented to ensure continued safe and reliable operation. These programs should include visual inspections, electrical testing, and thermographic scanning to identify any potential problems before they become major issues. It is vital to keep accurate records of all maintenance and inspection activities to track the performance of the electrical system over time. When performing any electrical work in the chiller pump room, always follow safe work practices and use appropriate personal protective equipment, PPE. This includes wearing insulated gloves, safety glasses, and hearing protection. To energize and lock out, tag out all circuits before working on them. And be aware of the potential hazards associated with high-voltage electricity. In conclusion, the installation of high-voltage conduits in a chiller pump room requires careful attention to detail and adherence to all applicable codes and standards. By following the recommendations outlined above, and by working with qualified electrical professionals, it is possible to create a safe and reliable electrical system that will provide years of trouble-free operation. The importance of proper concrete encasement, grounding, bonding, and maintenance cannot be overstated. These measures are essential to protect personnel, equipment, and the overall integrity of the electrical system. Always prioritize safety and consult with experts to ensure that the installation meets all requirements. Furthermore, let's consider some specific details related to the conduit installation itself. Firstly, the type of conduit used should be appropriate for the application. Rigid metal conduit, RMC, is commonly used for high voltage applications due to its strength and durability. However, other types of conduit, such as intermediate metal conduit, IMC, or electrical metallic tubing, EMT, may be suitable depending on the specific requirements of the installation. Secondly, the size of the conduit should be selected based on the number and size of the conductors being installed. The National Electrical Code provides tables that specify the maximum number of conductors that can be installed in a given size of conduit. Thirdly, the conduit should be properly supported and secured to prevent movement or damage. Conduit support should be spaced in accordance with the National Electrical Code and should be made of corrosion-resistant materials. Fourthly, the conduit should be installed in a neat and workmanlike manner. Bends and offsets should be made using appropriate tools and techniques to avoid damaging the conduit. Fifthly, the conduit should be properly sealed to prevent the ingress of moisture or other contaminants. Conduit seal should be installed at all entry points to the building and at any other locations where moisture may be present. Sixthly, the conduit should be properly grounded and bonded to ensure electrical safety. Grounding conductors should be connected to the conduit at regular intervals and should be bonded to the building's grounding system. Seventhly, the conduit should be clearly labeled to identify the circuits it serves. Labels should be durable and easy to read. Eighthly, the conduit should be protected from physical damage. Where the conduit is exposed to vehicular traffic or other potential hazards, it should be protected by bollards, barriers, or other means. Ninthly, the conduit should be inspected regularly to ensure that it is in good condition. Any damage or deterioration should be promptly repaired. Tenthly, consider the potential for electromagnetic interference, EMI, from the high voltage conductors. Shielded conduit or other mitigation techniques may be necessary to minimize EMI.